Welcome all to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is Embedded Systems. Subject code is KOE 062, that is open elective. Today the topic that I am going to cover is Inter-Integrated Circuit Communication Protocol, that is I2C communication protocol. So, basically I2C is serial communication protocol. So, data is transferred bit by bit along a single wire. In serial communication, one bit at a time is transferred from transmitter to receiver side, and so is the case with I2C also. The line which will carry the bit is SDA line, like SPI, that is serial peripheral interface. I2C is synchronous. So, the output of the bits is synchronized to the sampling of bits by a clock signal shared between the master and the slave. That is, the receiver will sample the signals at the same clock frequency as that of the transmitter. So, both the transmitter and the receiver are synchronized with the same clock. So, the clock signal is always controlled by the master. That is the case. The similar is the case with SPI also. This I have already discussed in the previous lecture. I2C combines the best features of SPI and UARTs. SPI is serial peripheral interface and UART is universal asynchronous receiver transmitter. Both are the communication protocols. With I2C you can connect multiple slaves to a single master, like was the case with SPI also, or you can have multiple masters controlling the single or multiple slaves. So, different configurations are available in the case of I2C, that is single master is controlling the multiple slaves, or multiple master is controlling the single slave, or the multiple master is controlling the multiple slaves. So, basically there are three configurations available with I2C. So, this is an advantage over the previous SPI protocol. This is really useful when we want to have more than one microcontroller logging data to a single memory card or displaying text to a single LCD. So, this is the case when multiple masters are controlling a single slave. So, this is a special case and this is very beneficial when a single microcontroller wants to control the multiple microcontrollers wants to control the single peripheral device. Like UART communication, this is another advantage with I2C as compared to SPI, that in I2C only two wires are used for data transmission. But this was not the case with SPI. In a SPI, as all of you must be remembering, that there were 4 signals, that was MOSI, MISO, clock signal and slave select signal. So, the number of wires required in the case of SPI was much more than that required in I2C. So, this is another advantage with I2C as compared to SPI. So, there are basically 2 wires, that is the 2 lines we can say, that is SDA, that is known as serial data line. The line is used for the master and the slave to send and receive the data. So, this is the single line which is used to communicate in both the directions, that is between transmitter and receiver. So, this line is used in the full duplex mode. Another line is serial clock. The line that carries the clock signal is the serial clock. So, here exact figure is shown for the master and the slave. So, there are only 2 lines SDA in both the master and the slave and HCL in both the master and slave. So, SDA is connected to SDA and clock signal is connected to the clock with the clock of the slave. So, in this way only 2 lines are used for signal transmission between the receiver and the transmitter in case of I2C. How the I2C works? Without I2C, the data is transferred in messages, and these messages are broken up into frames of data. So, basically there is a bigger message, that is the frame, and that message is divided into multiple frames. Each message has an address frame that contains the binary address of the slave, and one or more data frames that contains the data being transmitted. So, basically there are two important things, that is the address frame and second is the data frame. So, here what is the role of the address frame? In SPI, as you remember that there was the slave select line. So, to select the particular slave, a particular unique address of that slave was sent on that slave, that each slave was having the slave select line, and according to the choice that which slave has to be selected, that particular slave was selected, that is by activating that particular slave select line. So, in this way the slave select line was used to select a particular slave, but in case of I2C there is no such slave select line. So, what will happen? Addressing will be used. So, in this case how the addressing is used? Each slave device is having a unique address. So, what will happen? Suppose a master wants to select a particular slave or having a unique address. So, what it will do, if a master is connected to multiple slaves, then how the addressing will take place? That master will send the address to each and every slave. Now, each and every slave knows what is its address. Now, each slave will compare its own address with the address that is sent from the master side. When that matching occurs. Now, suppose first slave is having the same address as that is sent by the master device, then it means the first slave is to be selected. So, it sends back the acknowledgement signal to the master. So, in this way addressing is useful in selecting a particular slave. The master also includes start and stop conditions, read or write bits, acknowledge or no acknowledgement bits between each data frame. So, this is a complete message, as we can see. This is the start bit, that is the start condition and stop condition. What is the start condition? That SDA line goes from high to low before the HCL line goes from high to low. So, this is the start condition, and the stop condition, that HCL line goes from low to high, then after that SDA line goes from low to high. This is the stop condition. So, first of all start condition is there, then the address frame. Address frame is having 7 to 10 bits. So, in this way the address is there for each and every slave device. Now, read or write bit. Read or write bit signifies that either the master wants to write the data or wants to receive the data. Similar is the case with the acknowledgement and no acknowledgement bit, that if the data frame has been address or the data frame has been received or not, this is how we are going to acknowledge. Another is the data frame, that is of 8 bits. Again, after each data frame there is acknowledgement and no acknowledgement bit, and finally there is the stop condition. We will have a look at each of these one by one. In the start condition, as I already told, SDA line switches from high to low before HCL line switches from high to low. That is, this is the SDA, and after that HCL will go from high to low. Then again stop condition, SDA line switches from low voltage to high voltage after the HCL line switches from low to high. That is, this is HCL, first HCL will go from low to high, then after that SDA will go from low to high. Address frame, a 7 or 10 bit of sequence, unique sequence to each slave that identifies the slave when the master wants to talk to it. So, address frame is basically the 7 to 10 bits of sequence which is sent from the master to the slave side to identify a particular slave which it wants to select. Read or write bit. The address frame includes a single bit at the end that informs the slave whether the master wants to write the data to it or receive data from it. If the master wants to send data to the slave, then the read or write bit is low voltage level. If the master is requesting data from the slave, the bit is a high voltage level. This we have to note that if the writing is being done, then read or write will be bit will be low, and if the reading is to be done, then read or write bit will be high. So, this we have to note. Now, second is the acknowledgement or no acknowledgement bit. Each frame in a message is followed by an acknowledgement or no acknowledgement bit. If an address frame or the data frame was successfully received by the slave, then an acknowledgement bit is returned to the sender from the receiving device. So, this is how the sender gets the acknowledgement signal that yes, the message that the frame transmitted from the sender to the receiver side has been successfully received. I2C does not have slave select line. So, it needs another way to let the slave know that the data is being sent to it and not another slave. This I have already discussed about the addressing. It does this by addressing. The address frame is always the first frame, since the master has to first select the slave to which it wants to communicate. So, this is always the first thing that is to be done during communication, that the address frame is always the first frame which is sent during the transmission. So that the particular slave is selected according to the address that is sent by the sender to the receiver. The master sends the address of the slave it wants to communicate with to every slave connected to it. So, this is what is happening. Suppose this is the master, this is slave 1, slave 2, slave 3. Now, what is happening? Okay. So, this is the multiple masters, multiple slaves and single master. Now, this it is having, suppose it is having the address 0101011, slave 2 is having the address 10101011, and this is having the address 11110000. Now, what will happen? Suppose master wants to select this S2, slave 2. Now, it is broadcasting this address 1010101, because it knows the slave which I want to select is having this address. Now, it will send this address to all the slaves. Now, this slave will compare its own address with this address, it is not matching. Now, S2 will compare this address with its own address with this address, so it is matching. Similarly, this will compare with its own address with this address, it is not being matched. So, S2 will acknowledge the master that yes, I have received that I am the one which whom you wants to connect. So, in this way addressing helps in selecting the particular slave. Each slave then compares the address sent from the master to its own address. If the address matches, it sends a low voltage acknowledgement bit back to the master. If the address does not match, the slave does nothing and the SDA line remains high. So, how it will acknowledge? It will send a low voltage acknowledgement bit to the master. When we talk about the data frame, after the master detects the acknowledgement bit from the slave, now the slave has been selected, acknowledgement bit has been received from the master. Now, what will happen? The first data frame is ready to be sent. Now, the data frame will be transmitted. it is always 8 bits long and with the most significant bit is sent first. Each data frame is immediately followed by an acknowledgement bit to verify that the frame has been received successfully. This I have already shown previously, that here after each data frame acknowledgement bit is there. So, after successful reception of the data frame, acknowledgement bit is sent from the receiver to the sender side. The acknowledgement bit must be received by either the master or the slave depending upon who is sending. Since we already know that SDA line is used to send or receive the data to and fro between the sender and the receiver. So, this is bidirectional line between the sender and the receiver. So, data transmission can take place on either direction. So, if the direction of the data transmission is from sender to receiver, that is from the master to slave, then the acknowledgement bit is sent from the slave to the master side. And if the data transmission takes place from the receiver to sender, that is from the slave to master, then acknowledgement bit is sent from the master side to the slave side. So, this is what is written here. After all of the data frames have been sent, the master can send a stop condition. Now, suppose all the data frames has been successfully delivered and has been successfully received by the slave device. Now, what is the last thing? Last thing is the stop condition. So, similar to the start condition, we need to stop sending the data also. The stop condition is denoted by the low to high HCL line followed by the low to high SDA line. The stop condition is a voltage transmission from low to high on the SDA line after a low to high on the HCL line, with the HCL line remaining high. So, this is how the data transmission stops. Now, the master sends the start condition to every, this is shown that how the data transmission actually takes place. Now, start condition is this: master sends the start condition to every connected slave by switching the SDA line from high to low before switching the HCL from high to low. So, this is what is happening. SDA line is switching from high to low, and then after that HCL line is switching from high to low. Look from this side, high to low, high to low. Now, next, so to every slave device, this high to low transition is sent from the master to the slave direction. Now, second thing, the master sends each slave the 7 or 10 bit address of the slave it wants to communicate with along with the write or read bit. Now, what is happening? Another thing was the sending of the transmission of the data address frame, so in order to select the particular slave. Now, what is happening? A particular address is sent, that is 01010101. This is the address of the address that is sent from the master to the slave side. To each and every slave it has been sent. Now, the slave with the exact address will be selected. So, this is the slave which is having the exact address which has been sent from the master side. So, this slave will be selected, and these slaves are not having the matching. Each slave then compares the address sent, as I have already told, and this will be selected. Each slave compares the address sent from the master to its own address, and if the matches occurs, the slave returns the acknowledgement bit by pulling the SDA line low from 1 bit for 1 bit. So, this is how it gives the acknowledgement. This is the acknowledgement signal, that it will pull the signal low on the SDA line for only 1 bit. This is how the acknowledgement is sent from the slave to the master side. If the address from the master does not match the slave's own address, the slave leaves the SDA line high. So, in other cases, SDA line is as it is, high. The master sends or receives the data frame. So, after that, after selection of the slave device, after receiving of the acknowledgement bit, the data frame is sent. So, this is the data frame. This is the data which has been sent from the master to the receiver side. After each data frame has been transferred, the receiving device returns another acknowledgement. So, after the slave selection as well as after the reception of the data frame, acknowledgement signal is sent. So, again the acknowledgement bit is sent from the slave to the master side. Now, The last condition, that is to stop the data transmission, the master sends a stop condition to the slave by switching HCL high before switching HCL high. So, this was the stop condition, that HCL will go from low to high, followed by SDA going from low to high. So, this is the stop condition, and after the successful transmission of all the data frames, this stop condition is transmitted from the master to the slave side. Now, when we talk about the different configurations used in I2C protocol, so I have already discussed that multiple masters with multiple slaves can be used, but what is the problem with the multiple masters? So, this is the exact configuration. So, suppose 2 masters are there and 2 slaves are there. So, this is what is happening. So, in this way both the masters are connected to all the 3 slaves. So, now what will happen? The problem will occur when the multiple masters in the same system comes when 2 masters try to send or receive the data at the same time. Now, suppose both these masters tries to send or receive the data at the same time. Now, how will the problem be solved? Before sending any data, each master needs to detect if the SDA line is low or high. If the SDA line is low, this means that another master has the control of the bus. So, suppose it wants to communicate with the 3 slaves. Now, since another master is also connected to all the 3 slaves, so this master before sending or receiving the data has to check if the SDA line is low or high. If it is low, then it means another master is having the control of the bus. If it is high, then it can successfully transmit the data. If the SDA line is high, then it is safe to transmit the message. So, this is how the problem of multiple masters and multiple slaves is solved. So, this is how it is done, and this is the pull up registers. In this way this configuration is possible. When we talk about the advantages, only 2 wires are used. This is very good advantage. It supports the multiple masters and multiple slaves. This was not the case with SPI before. Acknowledgement and no acknowledgement bit gives the confirmation that each frame is transferred successfully, which this was not possible in SPI. Hardware is less complicated than UARTs, well known and widely used protocol. So, all these are the advantages of SPI I2C over other communication protocols. When we talk about the disadvantages, it is having the slower data transfer rate, because we know that the same line is used for the transmission in both the directions. So, this obviously the data transfer will get slow. The size of the data frame is limited to 8 bits. More complicated hardware is needed to implement the I2C than as compared to SPI. When we talk about the applications, so the common applications are the describing connectable devices via small ROM configuration tables to enable plug and play operation, such as in serial presence detect, that is SPD, EEPROMs on dual inline memory modules, that is DIMMs, and extended display identification data EDID for monitors via VGA, VDI and HDMI connectors. Another example is system management for PC systems via SMBus. So, as we all know that SMBus is directly following the protocol, that is the I2C protocol. Accessing real time clocks and NVRAM chips, that is a non-volatile RAM chips that keep user settings. So, again I2C is used in that case. Another good examples are accessing low speed DECs and ADCs, changing contrast, hue and color balance settings in monitors, changing sound volumes in intelligent speakers, controlling small OLEDs or LCD displays, reading the hardware monitors and diagnostic sensors, that is fans speed, turning on the turning off the power supply of the system components. All these are possible with SPI protocol, I2C protocol. So, in this way, as we see that I2C protocol is far better in some certain cases from SPI protocol, but yes, it has the disadvantages also. We will further study the different protocols in further lectures.